equals 5. But that is only true, it only fits the algebraic definition of a radical if b, which is 5, squared is equal to a, which is our radicand, 25. Okay. So this formal algebraic definition just proves, it shows that these are inverse operations. This is only true if this is true and vice versa. Okay. All right, so working with perfect squares. The idea with a perfect square, we know it's a perfect square if it has twin factors. Put that in quotes because it's not, it's sort of an informal way to say it. It's not a mathematical term. And the idea is if it has twin factors, one of the twins is the root. Okay. So, for example, starting with exponents, here are twin factors. A number times itself. These are twins, 3 times 3. Okay? They're factors because it's multiplication, and they're twins because they match. 3 times 3 is another way to write that with exponents, because all exponent is repeated multiplication, 3 squared, which equals 9. Now reversing that process, and this is going to seem a little, maybe tortured isn't the right word, but a little like overkill, but once we start putting in variables, this very principle I'm about to show is exactly what's going to allow you to do the simplify variables with ease. The idea is that if you, reversing this process, if you have the square root of 9, that means 9 is a perfect square because it has twin factors. Now, there are often other factor pairs. Of course, 1 times 9, for example, and in other bigger numbers have lots of factor pairs. But the only real way it's a perfect square is if it has twin factors, and then one of those twins is your root. Now, this is basically writing it as a product. We're writing our radicand as a product. Okay? I'm pointing that word because it's like using a reverse product rule when we get to ones with variables and exponents. Another way to write it is as a reverse power. 9 is the same thing as 3 squared. Now, before we go further, let me point this out. I said that little raised number in front of a radical sign is your index. What's our index here? 2, right. A lot of people say 1. That's a natural thing because we always say, you don't have to write when 1 is a coefficient, you don't have to write it. When 1 is an exponent, you don't have to write it. So you think, if we don't have to write it, it's a 1. Not in this case. We assume this is a square root. That makes an index of 2. It's the opposite of the square. Okay? So this is a square root. Okay? Now, you don't have to write that 2 as an index, but you can put it in to see the math I'm about to do. These are inverse operations, and inverse operations cancel each other out. So if you write your radicand as a power of whatever the index is, then basically that cancels out, and there's your answer. Okay? So if you can rewrite whatever your radicand is as a power that matches the index, then they will cancel each other out, and whatever you wrote in parentheses is rooted and released. Notice there's no more radical sign. Now, before we end today, we're going to have things where we can root and release part of it, but some is left behind, and you'll still have a radical sign. But right now, we're just rooting and releasing everything. Okay, so let's look at some general square root examples and principles. Square root of 0. Yeah. Square root of 0 times itself however many times. Still 0. 0 times 0, it's got twins. What about square root of 1? Same thing. 1 is a perfect root, a perfect square root, a perfect cube root, a perfect fourth root, everything. Because 1 times 1 times 1, no matter how many times, its root is 1. Okay? It has twin factors, triplet factors, quadruplet factors, quintuplet factors, etc. Okay? All right, so let's look at this general principle here where you can see what's different about these, and that changes everything. Square root of 81 is 9. It has twin factors of 9 times 9. Now that is the principal square root. That's what we assume. But there is another square root. There is another way to get 81 besides 9 times 9. The other way is, negative 9 times negative 9. Okay, so if we want that square root, we have to be told so with the negative on the outside. Here we're being told take the negative square root, which is, this is like negative 1 basically times square root of 81, which is 9. So we have negative 9. We got our negative square root. Now what this is basically saying is my twins here are 9 times 9. This is a way of saying my twins are negative 9 times negative 9. Okay? We assume we do this unless we're told this, and then our twins are the negative version. Negative times negative, it still equals positive 81. Okay. What about when the negative is under here? What twins will make negative 81? 9 times 9 is 81, positive. Positive times negative makes 81. The only way to get negative 81 with twins is negative times positive, right? Negative 9 times positive 9. Are those twins? No, I mean they're both 9, but one's positive, one's negative, right? So if this is a negative number, do you have twins? No. I mean there's 9 and 9, but if one's positive, one's negative, they're not twins. Okay? You cannot have a negative radicand. Not when your index is a square root. Okay? We're going to see some exceptions as we move forward, but for square roots, that is not possible.
You add, you know how like in the other units we do like a positive one, like a negative one to change the outcome number? Could we do that with the negative 81?
Oh, so like we change this to negative 1 times positive 81?
No, well that too, like the negative 9 times the negative, well, yeah, like just put the negative 1 in front, like multiply the numbers.
Yes. That's what's going to happen in our next unit. Because if we change this to negative 1 times positive 81, then we can root and release the positive 81 as 9, but we're left with the square root of negative 1.
Yeah, that's what I was.
Yeah. And the square root of negative 1 is I. It's imaginary. So we're about to move out of the realm of real numbers into imaginary numbers. Now, as I pointed out on our calendar, 11.7 is complex numbers, which involves imaginary numbers, and I always move that to the next unit. Okay? So this unit, if you see a negative radicand, a square root of a negative radicand, your answer is just that it's non-real. Okay? In the next unit, you'll tell me that this is actually equal to 9i. Okay? But that's a little down the road. So yes, there's a way to deal with it, but not in the realm of real numbers, and we're sticking with real numbers for now. Okay? So if you look at this in the calculator, if I do square root of 81, I get 9. If I do negative, to push the negative sign first, and then square root of 81, I get negative 9. My principal square root, my negative square root. But if I do second square root, if I do negative 81 under the radical sign, then it tells me error. And it tells me it's a non-real answer. So this, we're going to learn how to deal with it in the next unit in a different way, but for now, in our realm of real numbers, we just answer that this is non-real. Okay, so let's deal with variables here. Okay. Variables are also square, they've got exponents, so we can also unsquare them. In this case, we're working with square roots, and we'll look at other indices as well. So a square root, this is where we're really focusing on using our reverse product and or our reverse Prowler rule. Okay, we're going to reverse the process. Now, just like we sort of pointed out here, and let's look at this is kind of a matter of subtraction. Okay. So I could turn this into 10 and 2. Now, if I wanted to turn it into twins, what would I use? 6 and 6, right? X to the 6 times x to the 6 would be x to the 12. And then I'd have twins. So is this a perfect square?
Oh, yes.
Yeah, because it has twin factors. It has other factors too, but it also has twin factors, x to the 6 times x to the 6th. Okay. Here, I turn this into a square, and so this proves that it's a perfect square. It's a perfect square of x to the 7th squared. This means x to the 7th times x to the 7th. Its twin factors are x to the 7th times x to the 7th. Now, if you write that as x to the 7th times x to the 7th, you have x to the 7 plus 7, x to the 14th. You can turn it into, this is just a shorthand way to write the product rule. Okay, x to the 6 times x to the 6, or x to the 7 times x to the 7th. Now, these are both perfect squares because they are divisible by 2. You can break them in half. You can divide them by 2. They are even numbers. Okay? So if our index is 2, square root, index of 2, then you can break these into two groups. You can break any even number into two groups. You can break any even number into twins. Then you've got a perfect square. So is x to the 8th a perfect square? Yeah, because you can break 8 in half. Okay. So one way to write this is as reverse product rule, x to the 4th times x to the 4th. That's 4 plus 4 is 8. And then we have twins, so one of our twins is the root. Now another way to write it, a way that's a little more efficient, especially as we get into bigger and bigger looking problems with more variables, is to reverse the power rule instead. So if we write this square root, and we're going to write x in parentheses, but leave a blank, and put a square on the outside. We want to change x to the 8th into x to the something squared. And I'm also going to write, even though I don't have to, for the math, I'm going to write the little square on the outside, my index of 2. Because see, the reason I want this outside exponent to match my index, because then they'll be able to cancel out. So my job is to find out what would make this true. I don't want to change the value. What exponent would I put there so this will still be x to the 8th? 4. Because by the power rule, multiply. And the reverse power rule means divide. Divide 8 divided by the index of 2. 8 divided by 2 gives us 4. We broke it in half. Okay? So either way, either one of the twins or, with the power rule, the parentheses, the base, because those now cancel out. And so either way, we're left with x to the 4th. Square root of x to the 8th is x to the 4th. Okay. Now here we have a number and a variable. Is that number a perfect square? Yes. Is x to the 10th a perfect square? Yes. Yeah. If it's an even exponent, break it in 2. Okay. So we can either write this as 2x to the 5th times 2x to the 5th. Because that unsquared is 2. 2 times 2 is 4. And x to the 5th times x to the 5th is 5 plus 5 is 10. Okay. Now I'm showing that to show how that product and power rule are related, but really this is the more efficient way, and the way I'm going to be demonstrating them moving forward, is that I write the radical sign with its index, and I put in a 2 even if I don't have to, and then I look at the number, and I'm going to put a parenthesis with a square, because whatever my index is, I want that to match. And then I look at my variable, which is an x, so I put a parenthesis with an x, and I leave a space, and I put a 2. So I set it up so I have the number and any variables in parentheses with the index as the matching exponent on the outside. And then I make it true. What squared is 4? 2. What squared, x to the what is squared is x to the 10th? 5, right. And then that means my index and exponents cancel out, and what's in parentheses is my answer. There were no leftover bits. By the end of class, we're going to see where there are some leftover bits that stay under the radical. But if everything cancels out, if all the index and exponents cancel out, you have rooted and released, and there's no more radical. And your answer is 2x to the 5th.
Can we skip all those steps if you recognize?
Yes, for these simpler ones, I want you to get to the point where you go, oh, 2x to the 5th. Okay? This first step right here where I showed the product rule, I'm going to start skipping that now. Okay, you don't have to show all of that. This is really like either or. This is the more efficient way, and it's what I'm going to use moving forward. I just want you to see how it's the same mathematical rule. Okay. So moving forward here, I note, oh, perfect square. First you want to note perfect square, perfect square, perfect square. This is a perfect square because this is one of our perfect squares. The numbers don't follow the product and quotient rules. Okay? That's just a perfect square. This is a perfect square because our index is 2, so those are even, and they can be divided into two groups. So I'll just write something squared, x something squared, y something squared, with an index of 2 that's going to cancel out. Now what goes here in this parenthesis? Did anyone automatically think 50? No. And if you did, that's okay. I mean, I'm not trying to call anyone out. You don't have to say so. But I'm just pointing this out as a red flag because that's very common. Because when you're dealing with these exponents, you're thinking, oh, I divide it in 2, I break it into 2. Then sort of your brain then goes, oh, I just divide that in 2 also. No, numbers no, do not follow those exponent rules. Okay? You're unsquaring the 100. You're not dividing it by 2. This is not 50 squared, which would be 2,500. Okay? This is 10 squared. It has to match what this is. It has to have the same value. Okay? Now it's the exponents that you're basically dividing by 2. Because to make this true, this has to be, and this has to be 1. Right. Now, when we write our answer now, we don't have to write the 1, but that follows the power rule. Now, our answer now is there because we were able to cancel out inverse operations, cancel out those 2's in the index. There's our answer in parentheses. 10 x to the 7th y. Now, if you recognize everything as perfect squares, and you're really efficient with that and you're getting to the right answer, if you go from here to here, great. What we're going to see before the end of class is times when there are leftover bits, parts that aren't perfect squares, and so having this method is going to be really useful, otherwise you can get lost in it really easily. What's releasable and what's trapped. Okay. Now, this right here does not say equal. That means approximate. Okay. 45, is it a perfect square? No. 45, if you square root 45, and just as a note, if you ever need to get back to your home screen, it's like, I'm trapped, just do second quit right there, always get you back to your home screen. So if I put in square root of 45, I'm going to get a decimal answer. Only perfect squares give you a positive number. Now, the calculator, based on whatever settings it is, basically cut this off or rounded it. But this goes on and on and on and on and on and on forever. Okay? This is like the number pi, which we use 3.14 for pi, but it's actually 3.141, it just goes on forever and it never ends. It's what's called an irrational number. Irrational because it is impossible to write it as a ratio. A ratio is just a fancy word for fraction. Okay? So this can't be written as a fraction, just like pi can't be. This has to be rounded. This is an irrational number because it never repeats and it never ends. If you do math enter, it won't give you a fraction because it can't give you a fraction because it's irrational. Okay? Any square root of a non-perfect square, any root of any non-perfect root, is irrational. So you cannot write, if you write something as a fraction, that's why I always have you give me an answer as a fraction because I don't want to risk any rounding or repeating. We do math with actual answers. This is an approximate answer. So you cannot write anything but a rounded answer for this. And we can't do the math with that. So if you're asked for an approximation, great. That means approximate answer. Unless you're told otherwise, I just default to rounding to the nearest hundredth. This is approximately 6.71. Okay? But you can't do the math with that. When you're asked to simplify this, I'm going to show you a way to simplify it so you get an exact answer, but it's still going to involve radical signs because it wasn't a perfect square. Okay? So don't do this and round unless you're asked specifically to. Now that is the value of it. If you think of 45 is not a perfect square, what is the biggest perfect square that's still less than 45? Think of your perfect squares, but don't go higher than 45. 36, right? So if you write square root of 36, and that's the biggest one less than 45, and then here's square root of 45, which is not a perfect square. What's the next perfect square after 45? 49. Now what's the square root of 36? And what's the square root of 49? 7. Notice how this is in between those two. Each square root you have gives you countable integers. So anything that's not a square root in between two of them is going to give you an in-between answer, which is going to be irrational. Okay. Questions? Okay. Let's move up to, got everything on there? Yeah. Let's move to higher roots. So that's all square roots. Okay. So next we'll look at both cube roots and then nth roots. Okay. So the definitions, like with square roots, same idea. It's all algebraic. Cube root of A is equal to B if and only if B cubed is equal to A. Put it in terms of numbers. For example, if we have the cube root of 8, and cube root, just like a square root means twin factors, cube root would mean triplet factors. Yeah. So what times what times what times itself equals 8? 2. Yeah. And so this is only true if B cubed is equal to A, which is our radicand, 8. And that is true. 2 times 2 times 2 is 8. Now, nth root just means anything bigger than 3. Okay? Just like we showed in the calculator too, you have to go to that nth root button for anything bigger than 3. Okay? You have to enter the index first. So here, I'll just use 5. It could be anything bigger than 3, of 243. And just as a little reminder, if I wanted the 5th root of something, I have to, in this case, you have to enter the index first because there's not a dedicated button. So an index of 5, then math, and choose number 5, which is the x or the nth root. There's no parentheses. So 243, don't hit the parenthesis automatically, I always do that, and just push enter, and we get 3. Because that's true if and only if 3 are b to the nth root, our index is 5, so to the 5th power, is equal to our radicand of 243. And yes, 3 raised to the 5th power is 243. Okay? They reverse each other. Okay. So, as mentioned, perfect cubes have triplet factors. Of course, any higher nth roots have that many factors. Quadruplet, this one would have quintuplet factors. 3 times 3 times 3 times 3 times 3. And of course, one of those factors is, just like with the square root, one of those factors is the root. Okay? So, for example, here's triplets. A number times itself 3 times, which of course can be written as 5 cubed. 5 times 5 times 5, 125. Now, breaking that down, both by the product and the power rule, if we have the cube root of 125, that's the same thing as 5 times 5 times 5 under the radical sign. We can break down anything into its factors. And if we can break it down into triplet factors, we can break it down into any factors. There's lots and lots of factors of 125. But if we can break it down into triplet factors, then one of those factors is the root. And that's the reverse product rule. By the reverse power rule, we've got an index of 3. And if we make that, if we write 125 as something cubed, then those cancel out, and we rooted and released. Okay? You're not going to see that in the textbook. That's kind of an informal phrase that I use. You're rooting and releasing, which I mean the radical sign goes away. When you cancel out the index with an exponent, poof, the radical sign disappears. You release the root. That's going to be important as we get to ones where not all of it is released. Some of it is trapped under the radical. Okay. Now, with perfect squares, we know we could not have a negative radical because the only way to get a negative radicand, because the only way to get a negative radicand would be a positive times a negative. And that's not twins. But can you multiply 3 negative numbers and get a negative?
Yes.
Right. If you've got an odd number of pairs, even numbers of negative signs always cancel out to positive. You can't get a negative answer. But odd numbers of negative signs, pairs cancel out to positive, but you got an extra negative sign. That makes the answer negative. So this means negative 2, put it in parentheses, cubed. Doesn't actually change the answer when your exponent is odd, but be consistent about bases. And that equals negative 8, right. 2 times 2 times 2 is 8. Negative 2 times negative 2 times negative 2 is negative 8. Okay. So if you are taking negative 8, the cube root of negative 8, is this real?
No. Yes.
The cube root, does it have triplets? Yeah. There are triplets of negative 8. It's not mixed signs. It's negative 2 times negative 2 times negative 2. Those are all triplets. They have the same number, same sign. And they do indeed equal negative 8. So one of those is the root. To write the same thing with the reverse power rule, we can write negative 8 as negative 2 cubed. An odd exponent means that if we have a negative base, we have a negative answer. Because we've got an extra negative sign that didn't cancel out. Now 3 and 3 match, so we root and release. So square roots cannot have a negative radicand. Cube roots absolutely can have a negative radicand. Okay. So important here, and this applies as we move up to higher roots. Okay. So if your index is a square root, but also if it's 4 or 6 or 8, etc., that means it is what kind of number?
It would be a positive.
Not positive, even. It'll always be positive, but if it's specifically an even number, 2, 4, 6, 8, etc., well, pairs of negatives always cancel out to positive, so you cannot have a negative radicand. It won't have any a negative radicand doesn't have twins. You only have positive times a negative. Those aren't twins. So if the index is even, then the radicand must be right. And let's be a little more specific, though, because 0 is also okay. So let's, instead of saying positive, let's be real specific and say non-negative, which means 0 or a positive number. So in most cases, positive. And as long as your radicand is non-negative, then your root will be a real number. If you have a negative radicand with an even index, then you're going to have a non-real answer. However, if the index is odd, that means pairs of negatives cancel out, but you've got an extra negative. Okay? Negative bases with an odd exponent give you a negative answer. And negative indices with a negative radicand give you a negative root. Not a problem. So if the index is odd, meaning cube root or any other odd number, 5, 7, 9, etc., then the radicand can be what?
Maybe.
Yeah, it could be anything, basically any real number. Meaning a positive number, negative number, 0, doesn't matter. Any real number is okay. No restrictions on the radicand, except for that it's real. If your index is odd. So when you're doing problems, simplifying things, you need to make a note. Is my index odd or even? Okay, because that changes the rules for the radicand. So there are some specifically cube root examples. Cube root of 1. Yeah, just like the square root of 1 is 1. Okay? 1 times 1 times 1. There's your triplets. Now, square root of negative 1 would be square root of negative 1. Error, right, yeah, non-real. Error on the calculator, non-real answer. But cube root of negative 1, is that okay?
Yes.
Yeah, because this means negative 1 times negative 1 times negative 1. There's triplets, and that equals negative 1. Cube root of 23, does it have triplet factors? Yeah, 3 times 3 times 3. Cube root of 27 is 3. And this negative on the outside means our answer is, yeah. And that would be perfectly fine if this is a square too. And negative on the outside means give me the negative. Now, that negative, that principal versus negative is really just a square root thing. Because, of course, with its cubes, it might be positive or negative. This just reverses the sign of whatever this is. Because this is a positive radicand, it's a positive 3. But it's made negative by the negative on the outside. Now, what about cube root of negative 27 where the negative's on the inside? Yeah, still negative 3. With an odd index, either way, it ends up negative. Now, what about negative cube root of negative 27? Positive, right, because this is negative 3 is your root times that negative 1 on the outside reverses it back to positive. So you won't get a non-real answer with cube roots. You just have to be careful of where are my negatives. Okay, now working with variables, just like with squares, our question was, is that exponent even? In other words, can it be broken into two groups, divisible by 2? Okay? So if it's an even exponent, the answer is yes, it's a perfect square. Okay? 8 broke into 4 and 4, or 4 times 2. 10 broke into 5 and 5, or 5 times 2. So it's a perfect square if your index is divisible by 2. In other words, even. It is a perfect cube if your exponent is divisible by 3. If you can break it into groups of 3, then it is a perfect root, in this case, cube root. Okay? And if it was a fifth root, is it divisible by 5? Is it a